Up to this point, starting from a fundamental principle has meant to us starting from Newton's second law. It's time for us to introduce a second very important principle that we can use to understand and to predict motion, the energy principle. Each of us has had some everyday experience with energy in different forms. For example, the electrical energy we're using to run the computer with which we view this lecture, or the chemical energy used to run different types of vehicles that we may have ridden for transportation. Because energy comes in many different forms and, even more importantly, can often be readily changed from one form to another, energy can be used to connect seemingly unrelated processes, not only in the physics of motion, but also in many other fields of science and engineering. In almost all cases, it's crucially important to keep track of energy changes. Here, we will typically need to look at the total system energy E and examine changes to E, delta E, of our system. The total system energy can change only through the interactions of the system with the surroundings, where interactions are described by the transfer of energy between the system and the surroundings. This is the central meaning of the energy principle. Notice something remarkable here. On the left-hand side of the energy principle, the changes to the total energy are described solely in terms of physical quantities and properties of the system, while the right-hand side of the energy principle describes something completely different: interactions with the surroundings. It's not obvious that these should be related, but countless observations and experiments tell us they are. That's what makes the energy principle a secret of the universe, right alongside Newton's second law. To understand how to use the energy principle to describe and to predict motion, we first need to discuss how to describe the total energy E. As we said, energy can come in many different forms, so we shouldn't be surprised that a given system could contain energy in a number of different forms. The total energy E will be the sum of these specific energies, so we need to start listing the different types of energies that are important for understanding motion. Let's start with one of these energies today. When a system of mass m is moving with some speed, then the system has a kinetic energy k given by 1/2 times the mass times the speed squared, which we can also write in terms of the magnitude of the momentum. A couple of notes here. First, energy is a scalar, so let's make sure we don't fall into the trap of trying to write energies using vectors. Second, in our discussion of energies, we're going to focus on motion that occurs at speeds less than the speed of light. Later in the course, time permitting, we'll discuss the case where objects move near the speed of light. In this case, we will need to revisit and refine our definitions of system energies, including the kinetic energy, and do so in a way that's consistent with Einstein's special theory of relativity. For now, let's try to compute the kinetic energy in this example. Here's how we can find the kinetic energy, where we make sure that we end up with a scalar quantity. From this, we can see that the dimensions of energy, including kinetic energy, are mass times length squared divided by time squared, with corresponding units in the SI system, kilograms, meters squared, per second squared. Note the unit of energy has a special name. It's called a joule. We will discuss other types of energies associated with a system in later lectures. For now, though, let's discuss how the energy principle would be applied in a case where the only system energy that can change is the kinetic energy. In other words, for this system, delta E is equal to delta K. For concreteness, you can think of a box as our system, or you are free to think up another example. What we have in mind is starting with the system when it is in some configuration or state, which we will label as the initial state, and comparing that with the same system when it is possibly in a different state or configuration, say the final state. Now typically the final state would occur at a different time than the initial state. However, for the energy principle, we don't need to be explicit about specifying the time between the states, unlike the case of Newton's second law, where we were very explicit about specifying delta t. Now, compare here means look at the change in the system energy, delta E, which, for this example, as we said, we can do by looking only at the kinetic energy change, delta K. What if the system's final speed is greater than the system's initial speed? Well, in that case, if the mass is unchanged, we know that the quantity 1/2 mv final squared minus 1/2 mv initial squared is positive, meaning delta K is positive, which means here the change in the system energy, delta E, is positive. The system gains energy. How can it do that? By the energy principle, this can only happen if there was energy transfer from the surroundings to the system. By the same token, if the system's final speed is less than the initial speed, then delta K and so delta E are negative. The system loses energy. By the energy principle, this can only happen if there was energy transfer from the system to the surroundings. Clearly, if we want to apply the energy principle, we're going to need to learn how to describe interactions between the system and the surroundings in terms of energy transfer. That's the topic for our next lecture.